Welcome back. In this video, we will be studying about types of microcontrollers. Microcontrollers are classified based on number of internal bus in a microcontroller unit, based on memory, based on the instruction set, and based on the memory architecture. Apart from these, microcontrollers can also be classified based on IC chip or VLSI core. When I say VLSI core, it can be either VHDL or it can be Verilog. Moving on to the types, the first type is number of bits. The first type under this is 8-bit, the next one 16-bit, 32-bit. Apart from this, we can also have 62-bit microcontrollers. When we say 8-bit microcontrollers, the internal bus for data transfer in the MCU will be 8-bit bus. And the ALU performs the arithmetic and logical operations on a byte at an instruction. Byte is 8 bits. That time, the MCU or the microcontroller unit is called 8-bit microcontroller. A very popular example for 8-bit microcontrollers are Intel's 8031 and 8051. 16-bit microcontroller. Then the internal bus for data transfer in a microcontroller unit is 16-bit bus, and the ALU performs all arithmetic and logical operations on the operand words, which is of 16 bits at the instruction. The microcontroller is said to be 16-bit microcontroller. So compared to 8-bit microcontroller, 16-bit microcontroller will provide greater precision and performance. Examples for 16-bit microcontroller includes Intel's 8096. 32-bit microcontroller. When the internal bus for data transfer in a microcontroller unit or MCU is 32-bit bus, and the ALU performs arithmetic and logical operations on operand words, which is of 32 bits at the instructions. The microcontroller unit is said to be 32-bit microcontroller. Examples for 32-bit microcontroller includes ARM7, ARM9, ARM11 processor-based microcontroller families. So it provides greater precision and performance compared to 16-bit and 8-bit microcontrollers. The main applications of this 32-bit microcontroller includes embedded computing systems, like mobile phones, MP3 audio systems, and others. Coming to 64-bit microcontroller, then the internal bus for data transfer in a microcontroller is 64-bit bus, and the ALU performs arithmetic and logical operations on operand words of 64 bits at the instruction. The MCU is said to be 64-bit microcontroller. The example for this is ARM Cortex AX series of processor-based microcontrollers. Moving on to the classification of microcontrollers based on memory, it can be classified into two types. One is embedded memory microcontroller and external memory microcontroller. As the name itself suggests, in embedded memory microcontroller, all the hardware and software units required by MCU is present in a single unit. So there is no requirement to interface any external devices. For example, a telephone handset circuit. External memory microcontroller, when entire memory or part of the memory is externally interfaced using an interfacing circuit, MCU is called as an external memory controller. For example, in 8031, program memory is externally interfaced, and 8051 has both internal memory and external program memory that can be interfaced. Next one is based on the instruction set. Based on the instruction set, the microcontroller can be classified as RISC and CISC. RISC stands for Reduced Instruction Set Computer and CISC stands for Complex Instruction Set Computer. So let us differentiate between RISC and CISC architecture. As the name itself suggests, in RISC architecture, we will have less number of instructions, whereas in CISC, we have more number of instructions. Since we have less number of instructions in RISC, instructions are easier to understand. In CISC, it is reverse. Since there are more number of instructions, instructions are complex to understand. Next difference is in this architecture, each instruction in a single cycle, this will implement each instruction in a single cycle, and this is all done by hardwired control. Hardwired control and microprogram control will be starting in the next session. So each instruction is implemented in a single cycle using hardwired control. Whereas in a CISC architecture, the instruction is implemented using microprogrammed control. Going on to the next difference, clock cycle per instruction is less. Usually, it takes single clock cycle per instruction. Whereas in a CISC architecture, clock cycle per instruction, we can abbreviate clock cycle per instruction as CPI. We can say CPI is more for CISC architecture. The next difference is code density is more because code density is more for CISC architecture and code density is less for CISC architecture. See, in CISC architecture, the instruction size is fixed. If we say it is 32-bit, all the instructions, will, including opcode, operands, everything will be coded as 32 bits. In CISC, the number of the instruction size can vary. It can be 8 bits, it can be 16 bits, 32 bit, or 64 bit. So, since the instruction size varies, the code density is also more in case of CISC architecture compared to RISC architecture. So I can say RISC architecture has fixed length instructions, whereas CISC architecture has variable length instructions. The next difference is in CISC architecture, memory to memory operations are supported. So when I say memory to memory, let me take one example and explain. Memory to memory operations are supported. In RISC, no memory to memory operations are supported. Since it doesn't support memory to memory operations, we call it as load and store architecture. To understand this concept, let us take one small example. I will say I have a memory. Say, for example, I have a memory which has 4 rows or 4 columns and 2 rows. I will store some value called as A in the memory location and B in the memory location. If I want to perform addition operation on A and B and store the value of the addition into the location of A, then in the CISC architecture, I can just say add memory location A and B. Give the address of A and B, it should be done. But whereas when I want to execute the same thing in RISC, I will have to first load the value of A into some register. Let the register, I will call it as R0. First, I will have to load the value of A into the register, then load the value of B into another register, then perform addition of R0 and R1, and then store back the value of R0 into the location of A. So I'll just, this is what has to be done in RISC architecture. Going to eighth difference, in a RISC architecture, there is very less number of addressing modes. Since CISC supports even memory addressing, the operations that can be performed on memory, it requires more number of addressing modes. So RISC has less number of addressing modes. Whereas RISC has more number of addressing modes. Going on to next difference. Designing a pipeline stage or designing of pipelining is easier or simpler in case of RISC architecture, whereas it is complex in case of CISC architecture. So let's take one example. I have these instructions: move R0, R1, move R2, R3, add R2, R1. So what am I performing? I am moving contents of R1 to R0, moving contents of R3 to R2. Then I am adding contents of R1 and R2 and storing back in R2. If I have got to execute using a pipeline architecture, this operation will take, let's assume that it takes 3 cycles. One is to fetch the instruction, one is to decode the instruction, another one is to execute the instruction. These are performed by different hardware units. So if it is an unpipelined architecture, first fetch of this first instruction, decode of the first instruction, execute of the first instruction will be done. Then second fetch of the second instruction, decode of the second instruction, execute of the second instruction will happen. Then fetch of the third instruction, decode of third instruction, execution of the third instruction will happen. So if I assume that each operation takes 1 clock cycle, total 9 clock cycles are required. So what is happening? Each time if you observe, either of the units, hardware units, will remain unutilized. So in order to utilize all the units effectively, what we can do, when the first instruction is fetched and it moves on to decode instruction, we can start fetching the second instruction. When this first instruction moves on to execution stage, second instruction can go to decode stage. When second instruction goes to decode stage, we can fetch the next instruction. So this will reduce the number of clock cycles required. So this has many constraints, but let's not deal with all the constraints now. As of now, let's understand that pipelining will reduce the number of clock cycles required. So pipelining concept is simpler in case of RISC architecture, whereas it is complex in case of CISC architecture. To summarize the whole thing, the following points are to be noted for reduced instructions in computer. The MCU is said to be processing in RISC architecture when an instruction set supports a few addressing modes for the arithmetic and logical instructions and just a few load, store, push, pop instructions for data transfer. Second point, RISC provides no flexibility in choosing the many different ways of performing the arithmetic and logical operations. Third point, the operations are performed after load of operands into the registers, and the result of these operands are placed in the registers, and the register contents are later moved on to the memory. This is called as load store architecture. The next point, RISC implements each instruction in a single cycle using the hardwired control. Next point is to remember that it has less power dissipation and reduced instruction set. In next one, instructions are of fixed number of bytes and takes fixed amount of time for execution. Since the next point is to remember that since RISC architecture uses most of the times it uses registers of, for operation, it has more number of registers. The next one is the need for external fetches from the memories are greatly reduced in RISC architecture. The last point to remember is RISC provides higher performance in computing than CISC because of the little need for external switches, which takes significant amount of the processor time. Hence, it has got high performance. The performance also improves because of hardwired implementation of instructions. The classical example for RISC architecture is ARM processor family-based microcontrollers. To summarize CISC architecture, an instruction set that is supported will be having many addressing modes for arithmetic and logical instructions. There are many memory accesses during ALU operations and during data transfer instructions. CISC provides flexibility in choosing various ways of performing the data transfer, arithmetic, and other operations. Example, it is feasible to add contents of two registers or add the register and memory or add two memory addresses in a CISC architecture. The next point to remember is instructions are of variable number of bytes in CISC. These can take varying amounts of time intervals for execution. Classical example for CISC-based architecture is Intel's 8096. Next type of microcontroller division is based on whether it is a Harvard architecture or von Neumann architecture. The origin of Harvard and von Neumann architecture can be traced to the computing requirements for the US Navy. US Navy requested Harvard University and Princeton University to design a computing device. Both of them came out with the design, and that was named after the scientist who discovered it, and it is called as Harvard and von Neumann architecture. Coming to the first type, that is von Neumann architecture. Von Neumann architecture was found out by the chief scientist of Princeton University called as von Neumann. He devised a computer for the US Navy with the von Neumann architecture. In this architecture, the microcontroller unit had a common memory address space for both program memory and data memory. Hence, there was no separate control signals for data transfers to and from these two sets of memories. The architecture can be shown like this. See, it has a memory control unit abbreviated as MCU. Do not get confused with microcontroller unit. So it had a memory control unit. Then let me show memory space. It had a common memory for program, for data or variables, stack. So it was interfaced to control unit using these buses. The buses are data bus. Data is bidirectional bus. Then address bus. Address is always from a memory control unit. So address. Then the control bus. Control bus is always from a memory control unit. And the instructions that was fetched from the program memory was given to an instruction decoder. So this is the instruction decoder, and then it goes to CPU with registers. So this is the block level representation of von Neumann architecture. When an instruction is given, the instructions are encoded in numeric form and stored along with the data in the same memory. The control unit will execute the encoded instructions from memory. The instructions and data are implicitly distinguished only by the way they are used, and there is no significant way to tell the difference in the same stored memory. So as a conclusion, we can say in von Neumann architecture, program and data can be stored on the same memory chip or unit within the same address block. Going on to Harvard architecture, in this architecture, the memory control unit has a distinct memory address space for the program and data memory. Separate control signals for data transfer from data memory and program memory is required. The key features of this Harvard architecture includes CPU can read instructions and data at the same time. Right? Because we have two separate memories, one for data and one for the program. So both the instructions as well as data can be fetched from memory and executed simultaneously. Electronic hardware circuit in case of Harvard architecture was more complex. To draw the block representation, we can show something like this. It had program memory separate, program memory. From program memory, the instructions moves on to the instruction decoder. Address is issued by the instruction decoder, and the data is bidirectional. Data moves from program memory to instruction decoder. Control signals is issued from the instruction decoder. The instruction decoder can also interact with the stack, whereas CPU can fetch the data directly from the data memory. Again, address will be sent from the CPU. Data is bidirectional bus. Control will be sent from CPU. So please note, in von Neumann architecture, for instruction and data fetching, single shared bus is used, whereas in Harvard, separate buses for instruction and data fetching is used. This increases the speed of execution, but the processor design becomes complex. So in this video, we studied the various types of microcontrollers based on various parameters. Thank you.